What specific problem does your proposed method aim to address regarding self-verification in vision language models, VLMs? Can you articulate the gap in existing methods that your paper seeks to fill?
Our proposed method aims to address the limited self-verification capabilities in vision language models, VLMs, particularly during inference-time computation. We identify a significant gap where existing RL-trained VLMs struggle to effectively utilize visual information for self-verification, leading to a generation verification gap that is not present in large language models, LLMs. Our findings reveal that methods emphasizing self-verification, such as best-of-n sampling, do not outperform generation-heavy strategies like majority voting, indicating that VLMs are not adequately leveraging their multimodal inputs. Additionally, we observe that VLMs sometimes perform better in verification tasks when visual inputs are omitted, suggesting a reliance on textual information that undermines their verification process. This highlights the need for improved multimodal verification mechanisms in VLMs to enhance their reasoning performance, which our work seeks to address.
How does the proposed method, particularly the self-verified best-of-n approach, work? Illustrate it step by step, detailing how the model generates and verifies outputs.
The self-verified best-of-n approach operates by first generating multiple candidate outputs from the vision language model, VLM, based on a given input. Specifically, the model samples a set of diverse responses, which allows it to explore various potential answers. Next, the model acts as its own verifier by evaluating these generated candidates, scoring them based on internal measures of confidence, coherence, and contextual alignment. The output identified as the most reliable by the model itself is then selected as the final answer. This method emphasizes the model's self-verification capability, as its accuracy hinges on correctly identifying the best answer from the generated responses, integrating a reflective reasoning process into the output selection.
Could you provide a simple yet illustrative example that demonstrates the inner workings of your proposed algorithm? Walk through the main algorithm steps with a specific scenario in mind.
To illustrate the inner workings of our proposed algorithm, let's consider a scenario where a vision language model, VLM, is tasked with answering a geometric question based on an image and text prompt. The algorithm follows these main steps. 1. Input generation. The VLM receives an input consisting of an image of a geometric shape, e.g., a triangle, and a text question asking for the area of the triangle. 2. Candidate output generation. The model generates multiple candidate answers using the best-of-n sampling method, producing, for example, 3 outputs, 10, 12, and 15. 3. Self-verification. The model then evaluates these candidates. In the self-verification step, it uses its internal mechanisms to assess the correctness of each candidate. For instance, it might calculate the area based on the dimensions visible in the image and determine that 10 is the most plausible answer. 4. Final selection. The model selects the answer deemed most reliable based on its self-verification process, which in this case is 10, and outputs this as the final answer. 5. Performance evaluation. Finally, the model's performance is evaluated against the ground truth, which is known to be 10, confirming the accuracy of the self-verification process. This example highlights how the VLM utilizes its self-verification capabilities to refine its outputs. Although our findings indicate that current VLMs struggle with effectively leveraging visual information during this process, as noted in the paper.
What are the primary theoretical or practical advantages of using the self-verified best-of-n strategy over traditional decoding methods like majority vote?
The primary theoretical advantage of the self-verified best-of-n strategy over traditional decoding methods like majority vote lies in its emphasis on self-verification capabilities. While majority vote relies on the model's generation quality to produce multiple correct answers for consensus, self-verified best-of-n integrates a self-assessment mechanism where the model evaluates its own outputs to select the most reliable answer. This approach theoretically allows for a more nuanced understanding of the generated responses as it aims to leverage the model's internal verification processes. However, the practical findings in the paper indicate that, despite this theoretical advantage, the self-verified best-of-n strategy underperformed compared to majority vote across various evaluated RL-trained VLMs, highlighting a significant generation verification gap. This suggests that while the self-verified best-of-n strategy is designed to enhance reasoning through self-verification, its current implementation does not effectively translate into improved performance in VLMs, as they struggle with utilizing visual information during verification.
How did you validate the effectiveness of your proposed method? Explain the experimental design, datasets used, benchmarks or metrics for performance evaluation, and their significance.
To validate the effectiveness of our proposed method, we conducted extensive experiments using two datasets, GeoQA170K, which focuses on geometric reasoning with image-text pairs, and MathVista, encompassing a variety of visual question-answering tasks. We employed reasoning accuracy as our primary evaluation metric, defined as the proportion of examples where the final selected answer exactly matches the ground truth solution, emphasizing the model's ability to self-verify and select the best answer. Our experimental design included contrasting two inference-time strategies: majority vote, which aggregates multiple outputs to determine a consensus answer, and self-verified best-of-n, which uses the model itself to evaluate and select the most appropriate answer. The results indicated that majority vote consistently outperformed self-verified best-of-n, highlighting a generation verification gap in VLMs and suggesting that current models struggle with effective self-verification, particularly when visual information is included. This experimental framework and the observed performance metrics underscore the limitations of RL-trained VLMs in leveraging self-verification for improved reasoning.
What significant results did you achieve with your new method, and how do they compare with existing approaches in terms of reasoning performance?
Our study revealed that inference-time decoding strategies, particularly majority voting, significantly enhance reasoning performance in RL-tuned vision language models, VLMs, achieving consistent performance gains of 4.5% and 4.1% over the baseline greedy decoding. In contrast, self-verification methods, such as best-of-n sampling, underperformed, highlighting a generation verification gap where generation-heavy strategies outperformed verification-heavy ones. Notably, the emergence of aha moments in VLMs did not translate into improved reasoning accuracy, as evidenced by the lack of correlation between these moments and correct answers. Additionally, we found that VLMs sometimes performed better in self-verification tasks when visual input was omitted, indicating a failure to effectively leverage visual information. Overall, our findings suggest that current RL-trained VLMs struggle with self-verification, which limits their reasoning capabilities compared to existing approaches that emphasize generation quality.